In this video, we're going to talk about Bernoulli trials and binomial distributions. So to get started on this topic, let's think back to section 3.5 when we asked the following question. How many ways are there to get 2 heads in 4 coin flips? We have to choose which flips are heads. So the number of ways to do that, we're going to use a combination because it's an unordered selection. And of the 4 possible flips, we're going to choose 2 to be heads. So C42. If you work that out on your calculator, that's 6. And if you want to really convince yourself that 6 is the correct number, here we've written out the 6 possible ways to get 2 heads in 4 coin flips. So we're going to be using this idea quite a bit in this section. So a little bit of notation that's going to be helpful in this video. Instead of writing C and R, we're going to come up with a bit shorter piece of notation, and we're just going to write that NCR. So you'll write the big number first, then you write the C, then you write the smaller number. And we'll see that in the formula that we're using in this section, this shorter piece of notation here is going to be helpful. So in the new notation, instead of writing C 4, 2, as we would have in the old days back in section 3.5, we're no longer going to write that. Now we're just going to write something like 4C2 and put that into our calculator to get 6. So let's define what a Bernoulli trial is. It's an experiment with only 2 outcomes. And for simplicity, the 2 outcomes are usually called success and failure. Some notation to go along with a Bernoulli trial, we're going to let P represent the probability of success, and Q will be the probability of failure in our Bernoulli trial. Because you can only have a success or a failure, when you add up the probabilities, you're going to get 1. So P plus Q is going to equal 1. And if we rephrase that, you could say Q is going to be 1 minus P. So in other words, if you know the value of P, then you can quickly compute the value of Q because it's going to be 1 minus P. So let's say we roll a die and we consider success to be rolling a 4. So this is an example of a Bernoulli trial, because when you roll your die, one of 2 things can happen. You can have your success where you roll a 4, or you can have a failure, which would be where you roll anything else. So the question is to calculate P and Q. So we're really just checking whether we understand what P and Q are. So P is the probability of success. So the probability that the roll is a 4. And there's one way out of 6 to roll a 4 on a fair die. Then Q is our probability of failure. So that would be probability that the roll is not a 4. The quick way to calculate Q is you just think it's going to be 1 minus P. So in other words, Q is going to be 1 minus 1 out of 6. So that's like 6 out of 6 minus 1 out of 6 is 5 out of 6. And there we've got our probabilities of success, 1 out of 6, and probability of failure, 5 out of 6. So now we can define a binomial experiment, and this is really what we care about in this section. Binomial experiment is a sequence of n independent Bernoulli trials. So let's look at this word independent here. Independent just means one trial does not affect the others. So a classic example could be something like if you roll a die a bunch of times. What happens on the first roll does not affect what happens on the second or the third roll. So the rolls of the die are independent. So a binomial experiment is just when you do a bunch of these independent Bernoulli trials, something like rolling a die or flipping a coin over and over and over again. And the symbol that we're going to use to represent how many of these trials that we're doing is n. So let's say that we roll a die 7 times, and we consider a success to be that a roll is less than 3. Based on that, we're going to calculate n, p, and q. All right, so this is an example of a binomial experiment. So binomial experiment is where you do something over and over and over again. In this case, it's rolling the die repeatedly. And each trial, so each time you roll the die, one of 2 things can happen. You can have a success where your roll is less than 3, or you can have a failure where your roll is 3 or greater. So it's a sequence of success-failure trials. All right, let's see if we can calculate N, P, and Q. So N represents the number of trials. So that's the number of times that you're doing this repeated process. In this case, it would be 7 because we're rolling the die 7 times. P is our probability of success on a single trial. So we just have to ask ourselves, what's the probability that a roll is less than 3? So you're just thinking now about one roll of the die and asking yourself, what's the probability that the roll is less than 3? Well, rolls that would satisfy that would be a roll of 1 or a roll of 2. So that would be 2 ways out of 6. So let's call that 2 out of 6, or better, let's call it 1 out of 3. And then to get Q, you're just always going 1 minus P. So 1 minus 1/3 is 3 out of 3 minus 1 out of 3, 2 out of 3. So now we're getting into the main formula for this section. The formula tells us how to calculate the probability of getting exactly X successes in a binomial experiment. And here's our formula. The probability of getting X successes is NCX times P to the X times Q to the N minus X. And I'll talk a little bit later in the video about where exactly this formula comes from. So for now, let's just make sure that we understand what all the symbols are. So N is the number of trials. P is the probability of success on a single trial. And Q is 1 minus P. So let's say we roll a die 5 times, and we're going to find the probability that we get exactly 3 2s. So first thing I would point out is that this is a binomial experiment. So I'm just going to write down our keyword binomial. And the way we recognize that is because we're doing something over and over and over again. In this case, it's rolling the die 5 times. So once you decide that it's a binomial experiment, then it's good to try to figure out what your N, P, and Q values are. So N represents your number of trials. That's the number of times you're doing this repeated process. So that'd be 5, because we're rolling the die 5 times. P represents a probability of success. Okay, so it's going to be the probability of whatever we're considering a success in this problem. And for that, we have to read the problem. We're trying to calculate the probability that we get exactly 3 2s. So what we're going to consider a success here is rolling a 2. Right? So to calculate P, we're just asking, what's the probability that we roll a 2 on a single roll of the die? Well, that would be 1 way out of 6. And then once you've got P, then you can get Q quickly by just saying it's going to be 1 minus P. So 1 minus 1 out of 6 would be like 6 out of 6 minus 1 out of 6 is 5 out of 6. Okay, so now we've got our numbers, N, P, and Q, that we're going to use for the problem. I also find it helpful to write down what X represents. So in general, X represents the number of successes, and what a success is going to vary depending on the problem. So we've said in this problem, what we're considering to be a success is rolling a 2. So let's say X is the number of 2s that are rolled. And the value of writing that down is now we can rephrase the question symbolically. We can say the probability that we get exactly 3 2s is the probability that X equals 3. Because what X is doing is recording the number of 2s that are rolled. So if we want to roll 3 2s, we're saying we want X to equal 3. All right, so we're going to try to calculate the probability that X equals 3. And to do that, we're going to use the formula that we just talked about a minute ago. So I think I'll write that down on the side of the screen here. The formula for these binomial problems is NCX. I'm going to put that in brackets. NCX times P to the X times Q to the N minus X. So that's the formula that we're going to be plugging into. All right, so let's try it. So N is 5. And X is 3. So we're going to go 5C3 times P, 1 out of 6, gets raised to the power X. And then Q, which is 5 out of 6, gets raised to the power n minus x. All right, so I have to do a little bit of mental math here. N is 5, x is 3, so 5 minus 3 is 2. A fast way to think about these exponents is that when you look at the x and the n minus x, they're going to add up to whatever your n value is. So if I know n is 5 and I know this exponent is 3, then I can say, oh, whatever this number is, it's going to have to add up with 3 to make 5. So that's sort of a quick way to think about the exponents. All right, now to make your life easier, if you want, you could go to your calculator and just calculate this number in advance. On your calculator, that's 10. So this comes out to 0.03. In other words, you've got about a 3% chance that you get exactly 3 2s when you roll this die 5 times. Now let's put a part B on here and let's ask, find the probability that we get more than 3 2s. Okay, well, remember from our setup here that x is representing the number of 2s that are rolled. So if we wanted to rephrase this probability in terms of symbols, we would say this is the probability that x is more than 3, has to be strictly bigger than 3. And we can make that more specific because we know that we're only rolling this die 5 times. If x is bigger than 3, the possibilities are that x could be 4 or x could be 5. And that word or is just going to prompt us to add. So we're going to calculate the probability that x is 4, and then we're going to add that to the probability that x is 5. So this is like saying the probability of rolling 4 2s, and this is the probability of rolling 5 2s. So if we add those up, we've got the probability that we've got more than 3 2s that are being rolled. So our n value is still 5, so we're going 5c4 times p is 1 out of 6, so we go 1 over 6 to the 4 times 5 out of 6 to the, well, exponents are going to add up to 5 because your exponents always add up to n in this type of problem. Then we move on to the second term. It's going to be 5c5 times 1 out of 6 to the 5 times 5 out of 6 to the, well, again, exponents are going to add up to 5, so that's going to be 0. And then to make life easier when you go to your calculator, you can just figure out a few things in advance. So 5c4 is 5, 5c5 is 1, and also anything raised to the 0 is going to be 1. So you can basically cross that off and say that's 1. So now you've got something that's a little bit easier to type into your calculator. So trying that, you get 0.003, or if you want to write that as a percentage, that's 0.3%. So highly unlikely that we're going to get more than 3 2s when we roll this die 5 times. Let's do one final part here. Let's find the probability that we get less than 4 2s. So let's rephrase that symbolically. The number of 2s that we roll is represented by x, and we're saying we want that number to be less than 4. So if we break that into the cases, we would take the probability that x equals 0 plus the probability that x equals 1 plus the probability that x equals 2 plus the probability that x equals 3. And again, the reason that we're adding these probabilities is because we're saying x could be 0 or x could be 1 or x could be 2 or x could be 3. And or is the keyword that prompts us to add. Now, I don't really feel like doing 4 individual calculations if we can avoid it. So remember that the total probability of all the different scenarios has to add up to 1. So therefore you could say this is 1 minus the probabilities that we don't want. So let's think about the scenarios that we don't want. We don't want x to equal 4, and we don't want x to equal 5. So it's going to be good enough just to subtract off those probabilities. So I'm actually going to put brackets on here and say we're going to be subtracting off the sum of the probabilities that we don't want. And that will work particularly well because if you look back at part B, what we did in part B was we calculated the probability that x equal 4 or x equal 5, and we figured out that that sum was 0.003. So all we have to do now to finish the problem is go 1 minus that probability that we calculated in part B. So final answer then would be 0.997. So very good chance that we are going to get less than 4 2s when we roll this die 5 times. So let's talk briefly about where this formula comes from. We're calculating the probability of getting X successes when we do N trials. So first thing we're going to have to do is think about which X trials are successes. Is it the first X trials? Is it the last X trials? Is it every other trial? So we have to make that choice. And that comes from the very first problem that we talked about in this video. So remember, we talked about this problem of how many ways are there to get 2 heads in 4 coin flips. That's basically the same problem as how many ways are there to get 2 successes in 4 trials. And so we said you just use a combination. So that's where the NCX comes from. And often this looks more clear if we put brackets around that. So I'm just going to bracket there. Okay, then we have to calculate the probability of getting the X successes. Well, probability of a success is P. So basically we're going to go P times P times P times P. If there are X successes, fast way to write that is P to the X. And then we need to account for the likelihood of getting N minus X failures, because there are N trials in total. So if you've got X successes, then you know you're going to have N minus X failures. So probability of a failure is Q. If we have N minus X failures, then we're going to go Q times Q times Q times Q a bunch of times. So a faster way to say that is Q to the N minus X. So that's where that formula comes from. Probability of X successes. In a binomial experiment, you're going to do your NCX. I'm just going to make that C a little bit easier to read. So the NCX chooses which trials are successes, and then you account for the probability of the successes here, and then probability of failures here. So let's say a basketball player makes 65% of his free throws. He takes 3 shots and does not improve with practice. We're going to let capital X be a random variable. Specifically, it's the number of successful free throws that this player makes. And we're going to find the probability distribution of X. So first thing I would say to myself here is that this is a binomial experiment. I'm going to write down the keyword binomial, because we've got a process that's being repeated over and over and over again. In this case, it's the basketball player taking his shot. It is important here that he does not improve with practice, so that we know that his probability of success is the same on every single shot. So every trial is identical. Every time he takes a shot, he's got a 65% probability of making a successful shot. So now that we've decided that it's binomial, let's try to write down N, P, and Q. So N is the number of trials. In this case, it would be 3. So that's how many times he's taking his shots. P is the probability of success on a single trial. So probability that he makes his shot, 0.65. And then Q is 1 minus P. So that's going to be 0.35. So this is the probability that he makes his shot, and then the probability that he misses his shot. Okay, now we're told in the problem that the variable X represents the number of successful free throws. And what we're trying to do is find the probability distribution of X. So let's remember what this word probability distribution means. It means you want to come up with a table that lists your different X values and the probabilities of each of those X values. So if this guy's taking 3 shots and X represents the number of successful shots, he could have 0 successes, he could have 1, 2, or 3 successes. So we're going to have 4 rows in this table, and our goal is to figure out the probabilities that go with each of those values. So our probability is just going to come from that formula that we've been using for these binomial experiments, NCX times P to the X times Q to the N minus X. So little x here just represents whatever specific X value we're working with in that row. All right, so let's try our first calculation. I'm going to do this in red just to add some color here. So we're going to go NCX, so 3C0 times P to the X, 0.65 to the 0, times Q raised to some power. Okay, and then remember the exponents are just going to add up to N. So here we need the exponents to add up to 3. So as we go, let's put these numbers into our calculator. So you can make life easy by figuring out that 3C0 is 1. Also, anything raised to the 0 is going to be 1 as well. So it's just a matter of going 0.35 cubed. And let's round everything off to a couple decimal places just so we can see the percentages. So he's got a 4% chance of making 0 of his shots. So now for the second row, x is going to be 1. So we're going to have 3C1, 0.65 to the 1 times 0.35 squared. So 3C1 is going to be 3. You can put this whole thing into your calculator. It comes out to about 24%. So 24% chance that he makes one of his shots and misses the other 2. So continuing here, now x is going to be 2. So we're going to have 3C2 times 0.65 squared times 0.35 to the 1. Can work out your combination in advance. That's going to be 3. And your probability comes out to 0.44. Okay, and then last row, x is going to be 3 now. So we got 3C3 times 0.65 to the power 3 times 0.35 to the, well, exponents are going to add up to n. So that's going to be 0. And then doing a little bit of pre-calculation here, 3C3 is 1, and anything raised to the 0 is also 1. So really we're just doing 0.65 cubed, and that comes out to about 0.27. So the question was to find the probability distribution of x, and we've successfully done that because we've written out our different values of x and the probabilities that go with those. So just as an aside, I'm going to draw a picture so that we can get a visualization of how well this basketball player is performing. So we're going to draw a histogram. So a histogram, just a specific type of bar chart that you use when your variable x is numerical. So what we're going to do along the horizontal axis here is just list our different x values from the problem. So they were 0, 1, 2, 3. And then what we're going to do on the vertical axis is just graph our probabilities. And if we look back at our probabilities, they went up to about 44%. So if we just go up in increments of 0.1, that should be enough to fit everything on here. So we're just going to draw some bars centered over each of these x values here. So we said probability of the player making 0 successful shots was 4%. Probability that x equals 1, 24%. So about there. And then 44%. And then 27%. So 27%, a little bit higher, just slightly higher than what we had for this bar here. So drawing histograms won't be a huge part of our course, but it is just a nice aside since we put all that work into getting the probabilities. Now we've got a nice visualization of how this basketball player is likely to perform. So we've got the number of successful shots on the horizontal axis, and then we've got probabilities of each of those scenarios on the vertical axis. So let's recall the concept of expected value from our previous video. Expected value is also called the mean. So 2 words for the same thing, expected value or mean. We were using the symbol E of x for expected value in our previous video. But if you choose to call this mean instead, there's another symbol that's used interchangeably, which is the Greek letter mu. So you can either write E of x or you can write mu. They mean the same thing. You can say the word expected value or you can say the word mean. Again, they mean the same thing. So let's remember from our previous section how we actually calculate expected value. What we do is we take each x value, multiply it by the associated probability, and then we add up all those terms. So in our previous video, we were just calling that E of x. We've now introduced this shorter notation saying you can call that E of x or you can call that mu, either way. And we talked in our previous video about what that represents. It represents the theoretical average, so average being the key word here, theoretical average if the experiment is repeated infinitely many times. So you could imagine doing something like rolling a die, say 1,000 times, and just averaging your different rolls. So that would give you a pretty good indication as to what your expected value of a role is. But theoretically, you're taking that average over infinitely many trials rather than just 1,000 trials. So expected value gives you a really good sense of what the average outcome of an experiment is going to be. Now let's see how this relates to the binomial experiments that we've been talking about in this video. Here's our key fact. Let's let X be the number of successes in a binomial experiment. There's a really fast way to calculate the expected value, and that is, it's N times P. So it's your number of trials times the probability of success on a single trial. That gives you a really fast way of finding the average number of successes in a binomial experiment. So what's really important here is binomial experiment. So you have to be doing something like rolling a die a bunch of times or watching a basketball player take a bunch of shots. It has to be that kind of setup where you've got a binomial experiment in order to use this formula. So your company has to deliver 12 projects next week. Each project is independent and has an 80% chance of being completed on time. First thing we're going to do is find the probability that exactly 10 of these projects are completed on time. So first thing I would say to myself if I were faced with this problem is I would say, okay, let's try to identify what kind of problem it is. Could this be binomial? Well, yeah, it is, because we're looking at the projects one by one and we're saying, are you completed on time? Are you completed on time? Are you completed on time? So that is a binomial experiment. We're doing the same thing over and over again. To ensure that it's binomial, we can ask the question, what is N, P, and Q? And if we can figure those out, then we're on track with this binomial experiment. So number of trials would be 12. That's how many times we're looking at projects and figuring out whether they're going to be completed on time. It's important that the projects are independent. So if one project ends up being late, that is not going to have a cascading effect. It won't cause other projects to be late. So it's really important that you're doing something like rolling a die or flipping a coin where the individual rolls of the die are not affecting the later rolls. Similarly, a project being completed on time or being late is not affecting what's happening with the other projects. P represents the probability of success on a single trial. So in the context of this problem, that's the probability that a single project is on time. And we're told in the question, there's an 80% chance of that happening, so 0.8. And then Q is going to be 1 minus P, so Q is 0.2. So you got 0.8 for the probability that a single project is on time, and then 0.2, the probability that a single project is late. Okay, and then the number that we care about is how many are completed on time. So in general, X is going to be your number of successes, but it's better to frame that in terms of the actual problem and say that's the number that are on time, or number of projects that are on time. So that way we can rephrase the question. Instead of saying probability that exactly 10 are completed on time, we can say we're looking for the probability that X equals 10. Okay, from there we can break out our formula. So I think I'll write it down on the side here. NCX times P to the X times Q to the N minus X. So we'll just plug in all our numbers here. So we're gonna go 12C10 times 0.8 to the X, where X is 10, times Q to the, and the exponents are always gonna add up to N. So that's going to have to be 2 so that the exponents add up to 12. Okay, and then to make life a little easier, you could go to your calculator and just work out what 12C10 is if you want. Sometimes it's easier to work that out in advance. That works out to 66, and overall our probability is 0.28. So 28% chance that exactly 10 of these projects will be completed on time. So let's say we're a manager at this company and we just want to get a quick sense of how things are going. We might ask, what is the expected number that will be completed on time? Or that can be phrased differently as, what is the mean number that will be completed on time? Just two ways of saying exactly the same thing. Both expected and mean just refer to average. So we're saying, can we boil this down to an average number so that we have a sense of how many will likely be completed on time? Well, remember we said this is a binomial experiment because we're doing something over and over and over again. In this case, it's looking at our different projects and saying, are you going to be on time? Are you going to be on time? Is this project going to be on time? So because it's a binomial experiment, there's a very fast way of calculating the expected number of successes. The expected number of successes in a binomial experiment is always going to be n times p. So that only applies to binomial experiments. But when you have a binomial experiment, this is a super fast way of calculating the expected number of successes. So we're just going to say n is 12 and p is 0.8. So it's just a matter of multiplying 12 by 0.8 and getting 9.6. So on average, how many will be completed on time? 9.6. So as a manager, we'd say, okay, so that gives us a good sense that probably we're going to see something like 9 or 10 completed on time. That's likely what's going to happen. 22% of households in Victoria have pets. 10 households are randomly selected. We want to find the probability that at least 2 have pets. So this is another example of a binomial experiment. We are going around to these different households, 10 households that are randomly selected, and we're asking, do you have pets? Do you have pets? Do you have pets? So that's a repeated process or a set of repeated trials, and that makes it a binomial experiment. So once we've written down that keyword, let's see if we can figure out what n, p, and q are. So n is our number of trials. That would be 10, because that's how many times we're asking that question. P is a probability of success on a single trial. So in this case, a success is having a pet. So probability that a single household has pets, we're told in the question, it's 22%. So to say that 22% of households have pets is the same thing as saying, if you take a randomly chosen household, 22% probability that they have a pet. So 0.22. Q represents the probability that a household does not have a pet. So that would be 1 minus 0.22, which is 0.78. Okay, and then we can write down what X represents. So in general, for a binomial experiment, X is the number of successes. But specifically for this problem, it's the number of households with pets. Okay, and then that allows us to reframe the problem. So what we're looking for, we want the probability that at least 2 of these households have pets. So we want the probability that the number of households with pets is at least 2. So greater than or equal to 2. Now remember that there are 10 different households that we're surveying here. So if we were to break this into cases, we would say, well, X could be 2, or X could be 3, or X could be 4, or, and we'd have to go all the way up to our last case, X equal 10. And we would be adding up the probabilities for each of those cases. That's 9 different cases, and I definitely don't feel like doing that many calculations. So let's see if we can think of an indirect way of doing this. Because the probabilities of all the different scenarios are guaranteed to add up to 1, the other way to approach this is just to go 1 minus and then subtract off anything we don't want. So what do we not want? We don't want X to equal 0. So we're going to subtract off the probability that X equals 0. And we don't want X to equal 1. So we need to subtract off the probability that X equals 1. Once we've subtracted off both of these probabilities, then we're just left with the probability of the scenarios that we do want. Good, so now we're ready to do our calculation, and I think I'll write our formula just up at the top of the screen here. So NCX times P to the X times Q to the N minus X. So we're going to go 1 minus 10C0 times P to the 0 times Q to the, well, exponents are going to add up to N, which is 10. So that's going to be 10. And then we're going to go minus 10C1 times 0.22 to the 1 times 0.78 to the 9. Exponents are going to add up to 10 in each case. Okay, and then let's do a little bit of simplifying here. So 10C0 is 1. 0.22 to the 0 is 1. 10C1 is 10. So now we've got something that's a little bit easier to put into our calculator. And remember that both of these terms should be subtracted off because these are both cases that we're trying to discard or get rid of. So let's type everything into our calculator and we'll have our final probability here. It comes out to about 0.68. So about 68% chance that at least 2 of the households that we talk to will have pets. So that's our video on binomial experiments. Thanks for watching.